In this video, I will talk about how to estimate simple regression models in Stata. Before you watch this video, please make sure you have watched my previous video called Simple Regression Model. I have opened here the Stata program for Simple Regression Model and have executed part of it. So in this program, we will learn how to run a simple regression. Then we will learn about the predictions that we can do after a regression. We will talk about goodness of fit measure, the R squared, and then we will talk about various log forms that we can have. It uses two data files. One is a CEO salary data file, and another one is data file on wages. So as you download these files, please correct the path of where you put the data in order for the program to run. So to begin with, let's look at the simple regression and load the data with the CEO salary. So I will start by keeping only the two variables we need, salary and return on equity, dropping all of the rest. I will describe, summarize, and list the data. So here we have two variables, salary, which is in $1,000, and return on equity, that's actually measured in percent. If we summarize these two variables, we have that the average salary is being $1.2 million because the salary is measured in $1,000, and the return on equity, the average one, is 17%. And here's how the data looks like. The first 10 observations. We have, these are the salaries of the CEOs in $1,000. This is return on equity in percent. Let's explore the data a little bit. We can calculate the correlation between salary and return on equity. And here we see that that correlation coefficient is 11%. Or we could generate the mean of salary by using the egen command, and then we can also label this variable, say, average salary. In order to run a simple regression, what we need to do is type regress, or reg for shortly, and then put the value, put which is the dependent variable and which is the independent variable. So here we put salary as the dependent variable and return on equity as the independent variable. So here is how the regression output looks like in Stata, and we have seen this in the previous video. So we would concentrate on the two coefficients that we estimated here. The coefficient 18 is the coefficient for the return on equity variable. So how you would interpret this is that if return on equity increases by 1 unit, which the unit here is in percent, so if the return on equity increases by 1%, then salary would increase by 18 units, and this is $1,000. So the salary would be increasing by $18,000. That's how you interpret this coefficient. This is the intercept, and it shows what would be the CEO salary if the return on equity is 0. So after we run a regression, we can afterward plot the two variables that we have. So we can plot salary against return on equity with a scatter diagram. And LFIT calculates the fitted line for salary on the return on equity. So this is actually, this LFIT is the estimated regression line that we just estimated right here. So again, the formula for that is the predicted value of salary equals this intercept plus the slope times the return on equity. That is what this one is plotting. And graph two-way basically plots these two things. So let's go ahead and run this line. And here is how we have the scatter diagram. Here we have return on equity on the horizontal axis and then salary on the vertical axis, and we have the predicted line here. So these are the actual values of coming from the sample, and the predicted values are obviously on this line that we see right here. Okay, so let's do exactly the same thing with new data set on wages. So here we have data on wages. We are keeping only wage and education. By describing the data, we see the two variables, summarizing them. We have wage being on average hourly wage $5, and education on average is 12 years. And we can list the first few observations, list in 110, and basically see the wage and education here. So we can run a simple regression by saying regress or reg. Wage is the dependent variable, education is the independent variable, and this is the output that we see. We would concentrate on these coefficients again. This is the coefficient on education, or the so-called beta 1 hat, and this is the coefficient for the constant or the intercept, and that is the beta 0 hat. So how we would interpret this is if education increases by 1 year, then the wage would increase by $0.54. And this is the value of wage if education is equal to 0. Let's continue on with prediction after regression. And if you would like to get more help from Stata, you can type help predict at the command window here and then see a lot of the options that are available for after we estimate a regression. So we would be loading the data set again, running a regression, and then what this does is predicting. This is salary hat is the name that we're giving this new variable, and comma xb, that's the standard command for giving the predicted values back. So we can summarize the salary and salary hat and see how they look like, and then we can plot salary ROE against ROE in a scatter diagram, and then the salary hat and ROE. So let's see what happens. If I run this part of the file, what we see is here's the data, here's the regression, and we already saw this is the regression. We are predicting salary hat, which is the predicted values. And then if we summarize them, we see that the mean for the actual value of salary is exactly the same as the predicted value of salary. And that's not coincidental. The min max are different, so these are definitely different numbers, but the mean values are the same. If we plot these, then here these are the actual values of the dependent variable salary. And here, these are the predicted values of salary along this horizontal, along this line. This is the estimated regression line. So if we now want to predict the residuals, we would be using the predict command again, but comma residuals would give you the residuals. And we name these U hat. So again, this is a name we've given. This is a standard option after predict. We can summarize the salary and the U hat now, and we can plot the salary against ROE, and we can plot these residuals against ROE. So let's see what happens. So here we have gotten the residuals U hat, and here we have the same salary. This is the values of the salary. But if we're summarizing U hat, we're seeing that the mean is almost 0. And this is not coincidental because the residuals need to sum up to 0. This is one of the properties of the OLS estimators. If we use graph two-way to plot salary against ROE and then U hat against ROE, this is what we see here. So the blue dots here are the salary, and the residuals are actually the actual value minus the predicted value, so minus the values on the line. And now see that while the actual values would have a slope, that's the beta 1 hat coefficient, that's the slope. U hat, these are the residuals, they're actually centered around 0, so we effectively have flattened that curve around 0. So these are now the residuals that sum up to 0. If we list these, the first 10 observations, here are the return on equity and salary. This is the independent and dependent variable. Here's the salary hat. So these ones here are the values exactly on the regression line that we have. And the way to calculate these values here is by taking the intercept that we saw, the coefficient on the constant, plus we have the slope times the actual value of the ROE would be this predicted value. And then the actual minus the predicted value is this U hat. The actual minus the predicted value is this U hat, and so forth. So these are the U hats. So notice that if we take the average of this and the average of that, these two would have the same mean because salary and salary hat is basically predicting salary. If you take the mean of U hat or the average, that would be a 0. So now let's use the graph two-way by using scatter plot of salary against ROE, salary hat against ROE, so this is the line, and U hat against ROE, so these are the residuals. And then we could have the L fit, which is the line, the estimated line, regression line of salary against ROE. So if you type help two-way, you will see all of these options for the two-way command. And here we're putting little circles around. We're telling it what color to be each of these circles. So this is what you're seeing here. Let's run this command. And then this is the graph that we see. Again, these are the actual values are the black dots or the true values of the dependent variable. We have the L-fit line is this line. And then the yellow dots here are actually the predicted values. So if we have an actual value here, the predicted value would always be on the line. So this is an actual value, predicted value would be on the line here. So if we actually take an actual value minus the predicted value, we would be getting the residual. So if we have this is the actual value minus this predicted value, that is the residual that we get. And so again, notice this residuals right here are centered around 0. So as much as they are above 0, they would be below 0 because they need to sum up to 0. And again, the intercept here would be coming uh, at the value that we estimated with the model. This is 963, and the slope here would be 18. We can do the same things with wage. So we can estimate regression of wage on education. We can predict wage hat, which is the predicted value of the dependent variable common XB. This is the standard option after um, we estimated regression, and we can predict the U hat. This is a variable name we give it, and comma residual is for the residuals. And then we can graph in a scatter plot wage against education, the predicted value of wage, which is wage hat against education, and U hat the residuals against education, and L fit give the regression line of wage and education. So this is what we see here. So if we run a regression, these are the values of the coefficients that we have here. And these are the actual values for the wage. They're the blue ones. This is the estimated regression line. And the residuals are down here. So when we have an actual value minus the predicted value, that will be the residual right here. So again, the green dots are the residuals that need to sum up to 0. So notice again the slope of this line is exactly 0.54. This is that slope. This is the coefficient on education. So basically, how much does the wage change based on 1 unit change in education or 1 additional year of education? And this is what this slope is giving us. Next, let's talk about goodness of fit measures, or the R-square. And how we can calculate R-square is done in 2 different ways. So let me execute this code and then I will show you. So if we run a regression of salary on return on equity, we've seen this before. Now we're very interested in goodness of fit measure. This is the R-square. So the R-square is given here. It's 0.01. That is the R-square. But we can find it also ourselves because we know that the R-square is the sum of squares for the model, which is this number here, divided by the sum of squares total, which is this number here. So if you divide this number by this number, you should be getting the R-square for this regression. We can also call the R-square as a stored value. So if you would like to see more help on the e-return function, then you can just type it under help. But here's the list of all of the numbers that are stored after regression. So E of n is the number of observations. So here we have 209 observations. And you can see this is the number of observations here. And the other thing that we store is the R-square. And this value here for the R-square is exactly this value here. So these are actually stored in the program. So we could just call them by saying display our R-square, and that's the number, or display n for the number of observations, and this is the number that we have here. Same for the example with wage. We have the R squared is 0.16. This means that 16% of the variation is explained by the regression. The rest is due to error. So that is still a very low R square. And this number is equal to the sum of square model. So basically this number divided by sum of squares total. So this number, if you divide this by that, it would give you the R squared of 16%. If you call it with E of R2, that is actually this R square, and E of N is the number of observations, 526 is the same as this. So you can just display these two numbers using display R square and display E of N for the number of observations, and you can see this. Okay, so completely changing gears. Now we will talk about different log forms. So here's where we may want to use logs instead of the original variable. So what would that mean? So originally, what we did is we estimated a regression of salary on sales, and we could plot this with the scatter of salary against sales and put the fitted line here of salary against sales. But now we may want to transform either the salary or the sales in logs. And using logs actually helps us reduce the effects of outliers and has a lot of other desirable properties. So before we do that, if you would like to store all of these regression results neatly in a table, one thing that helps tremendously is the outreg2 package. So first of all, you can install the outreg2 package by going under Tools, Help, look for it, and then click on Install. And then if you use this command outreg2 using results.doc, it would give you all of the output nicely recorded in tables. And the first time you should use the replace. Later on, you can put comma append, and these results would be appended in the same table. So this is a very nice thing to do. Okay, well, this was a side note. So we happen to actually have logs in our data set, but if you don't have logs and you have the original variable sales, you could actually generate this by taking the log of sales and calling it a new variable, or the log of salary and calling it this new variable. So that's how you can generate logs. So we can, in order to estimate the log form, instead of regressing salary on sales, we would regress L salary, which was our logged variable, on L sales. Okay, so let's execute it up until here and see what happens. So here is the original linear regression that we saw before, and here is the scatter plot. So what you notice here is that as far as sales, we have some outliers here in terms of like really large values of X of our independent variable in comparison to the rest. So if we use logs, these would kind of get more together than being so far apart. And same for our Y variable for the salary. We still have some very large values that if we use logs would kind of bring them in together. So let's see what we use. If we use logs, we would estimate this regression and then plot it. Okay, so here is this new regression where we have log of sales and this is log of salary. So notice how we don't have these extreme values anymore. They're all more kind of like together, and the new transformed data looks like this, and this is the estimated regression line. And you could do this as well for if you want to log just the salary but not the sale. This is what we're going to get. So here we have the original X variable in millions, but the salary is in logs. So these values now got closer together, but these are still far apart. Or we can do the reverse, which is we can do the logs on the independent variable. And so if we run this, here's what we're going to find. So here we have the log of sales is our independent variable, but the dependent variable is in actual units. It's not logged. Okay, so if you look at the previous video, you could actually see how these coefficients are also interpreted. In a linear form, we interpret it as 1 unit increase in sales would bring zero point 0.1 units increase in Y. That's how you would interpret this, and you need to pay attention to what the units are. So sales are measured in $1 million. So for every $1 million increase in sales, this would bring $0.01 thousand dollars is how salary is measured. And that's what this coefficient is showing here. So the log-log interpretation is the easiest perhaps, is for 1% increase in sales, then we would have 0.25% increase in log salary. And then you can also check the interpretation here in the previous video, but here we have sales is for $1 million, whereas the salary would be increasing percentage, which would be 0.0015% increase in log salary. And here we have for each percent increase in salary, we would actually see the how much is the increase in salary, and that would be this coefficient here multiplied by 100. Okay, so finally, we would repeat the same thing for the wage example. So first we would estimate the regression of wage on education, and then here we would log the wage. Of course, we don't log the education because the education is measured in years. So here is the graph, the original regression of education, and this is wage, and that's how it looks like. We already talked about it, but if we have logs on education, we would find this. So here education is the original variable, and this is we have log of wage, and this would be how this new regression line looks like, and this is how the points here look like. So if you look at the results here in the original regression, we are saying that for 1 year increase in education, we have $0.54 increase in wages. But here, when we have logs, we would have to say for 1 year increase in education, we actually see 8.2% increase in wages. This is how we're going to interpret this coefficient. So with this said, we covered what we were planning to do for the simple linear regression by estimating the regressions, looking at the different predictions afterward, and also looking at the different log forms. Thank you for watching.